Basically, we have two types of things. We have something that looks like this. And then we have something that looks like this. And this thing on the left, this is what we call a definite integral. This is area under the curve. Y equal to f of x from A to B. So this was section 4.1 and 4.2. That was the hard way. And then in section 4.3, we learned the easy way. So you can look forward to that on Friday. Okay. What this next thing is called the indefinite integral. And it's also called the antiderivative. Okay. So what you're trying to do is you're trying to call this thing, this object right here, is the antiderivative. And when you take the derivative, you get f. So when you take the derivative, you get f of x. So let me give you some examples. I don't know why that thing is there. Oops. All right, now it's gone. So let's take a look at some examples right here. If I want the antiderivative of 2x, that's just going to be x squared, right? Because when I take the derivative of x squared, I get 2x back. So you'll also notice that if I put a 2x plus, if I put a x squared plus 7, this is still an antiderivative of 2x. Because when I take the derivative of this x squared plus 7, the derivative is going to be 2x plus 0, which is just 2x. So when I take the derivative of the antiderivative, I get the original thing back. All right. So you'll notice that it doesn't matter whether I put a 7 there or I put 52 there. The derivative of any constant is always going to give me 0. So what we do is we don't put a specific number, we put plus c. Okay. So this is a family of antiderivatives. Okay. So there were some basic things that were covered in the video. One of them is if you find the antiderivative of a constant, let's call this constant k, then the antiderivative is just going to be k times x plus any other constant c. Okay. And you could check that by taking the derivative of the right-hand side here. The derivative of kx is just k. The derivative constant is just 0. So we take the derivative of this, you just get the inside. All right. Your book at first avoids this indefinite integral notation, and they write the indefinite integral as capital F of x. So what your book would say is, if f of x is equal to k, then capital F, the antiderivative, is equal to kx plus c. So this guy right here is the antiderivative. So one thing you know is the antiderivative of a constant. The other thing that you know is, if you took the antiderivative of just x, you ask yourself, when I take the derivative, am I going to get x back? And what you'd see is that if you square x and then divide by 2, and then you add some constant, when you take the derivative of this right-hand side, the 2 comes down, and that cancels with the 2 in the denominator. So you're going to end up with just x. And the derivative of any constant is just 0. So you just end up with that, just the x. Okay. So after looking at these two examples, we come up with the reverse power law. In other words, if you had something like x to the n dx like this, what you could do is you could add 1 to the exponent and then divide by what you just wrote. And we can check this, right? Because when you take the derivative of that, what do you get? You bring down the n plus 1, so you got n plus 1 times x to the n. You subtract 1 from the exponent divided by n plus 1. And then those n plus 1s cancel each other out. So when you take the derivative of the right-hand side, you get this inside part. So the antiderivatives of the polynomial type things are pretty straightforward. So let's take a look at a couple more examples over here. So when I take a look at example 2, I can use the different properties to split this up into smaller pieces. So you don't necessarily have to split it up into smaller pieces. You can just find the antiderivative of each term. Maybe I'll just do it the easier way and just find the antiderivative of each term. Okay, so this is how I would do it. The 5 is going to stay there. So maybe I should have mentioned this constant multiple rule here. You know what? Since we just learned this properties of indefinite integrals, let me break this up into smaller pieces. So let me do it like this. This will be 5 times the integral of x to the 4th dx minus 7 times the integral of x cubed dx plus 4 times the integral of x dx minus 2 times the integral of 1 dx. If you wanted to use the sum, the difference, and the constant multiple rules. Okay. And then now that I have each of these pieces, I'm going to use that power law that I just showed you to find the antiderivative of these 3 terms. And then I can use the constant law to find the antiderivative of this guy. So this will be 5 times x to the 5th divided by 5. This one will be 7 times x to the 4th divided by 4. This one will be 4 times x squared divided by 2. And this will be minus 2x. And then because the antiderivative gives you a whole family of functions, we're going to tack on a plus c at the end there. Okay. So let me simplify this a little bit because it seems like we could do some simplification. So let me slide this over here and I'll put another equal sign. I'll just tighten it up a bit. So this is just x to the 5th minus 7 over 4 x to the 4th plus 2x squared minus 2x plus c. Is there any questions about this example here? No questions? All right. I have a question for you guys, actually. If you took a look at B over here, does anyone have any advice for how I should find the antiderivative of this inside piece? Any thoughts? No thoughts. Let me tell you what not to do. You can't find the antiderivative of the top and then the antiderivative of the bottom and then divide them. Jason says you want to get rid of this bottom part. How do we get rid of the bottom part, I guess, is my question.
you subtract it from like the top exponent, so it's like x squared minus like 1. I don't know how to explain it. Like I think it's factoring, but no wait, no, it's not. I don't know what it's called, but you just get rid of the bottom one.
I understand what you're saying. I'm going to help you out here. I could tell from what you're saying that you're basically saying you want to do this x squared over x plus 4x to the 1/3 over x like this dx. Is that what you meant, Jason? And
Yeah, and then you
then
just simplify.
you simplify, and as Yahir puts in the chat box, you want to write each of these guys in exponential form. So at this point, I should probably remind you that if you have two things with the same base, a to the m divided by a to the m, this is going to be a to the n minus m. So in this particular case, this is going to be x to the 2 minus 1 plus 4x to the 1/3 minus 1 dx. You just kind of stretch it out a little bit. And then this one becomes the integral of x dx plus 4 times the integral of x to the negative 2/3 dx. And now I can just find the antiderivative of each piece. Okay. So the antiderivative of the first piece, the antiderivative of the first piece is going to be x squared over 2. And the antiderivative of the second piece is going to be 4 times. Remember, we have to add 1 to the exponent this time. We're doing the opposite of what we did before. So you add 1, so this becomes to the 1/3, and then you got to divide by 1/3. Does that make sense? So you add 1 to the exponent, and then you divide by whatever number you just put there. That way, when you take the derivative, when you bring this power down in front, it's going to cancel with the thing on the bottom. Now, it's really unnatural to write something like this, just dividing by a fraction. So at this point, I want to remind you that if you have something like A divided by B divided by C like this, that's the same thing as A times C over B. So a lot of times you'll hear me say dividing by a fraction is the same thing as multiplying by the reciprocal. That's referring to this thing I just wrote on the left here. So this is dividing by a fraction. And then this part here is multiplying by the reciprocal. The idea is that these two things are equal. So let me finish off this example. We have a whole family of antiderivatives, and then I can just rewrite that as x squared over 2 plus 12 times x to the 1/3 plus c. Okay. And the great thing is you can always check your answer by just taking a derivative. So if you took the derivative of this guy right here, you should get the inside thing, which is the integrand. Now you would actually get this thing, you took the derivative, and you use algebra to manipulate it to get it back to this. Okay. Is there any questions about example B? Example B is one that, luckily Jason and Yahir told us that we should split this up into 2 pieces and simplify. That was good advice. Students sometimes make up their own crazy fake quotient rule to do this, and you can't do that. You can only differentiate, at this point, you can only differentiate like things that look like polynomials. All right. Does anybody have any brilliant suggestions for how I should do part C? Part C is kind of similar to part B, a little bit different flavor. I'm wondering if anyone has any advice for me. Yeah, here, you have any advice for me? Or anyone? How about if I told you what not to do? Don't create some fake product rule. I see two things multiplied here, but you only know how to take the derivative of the antiderivative of something to the nth power, right? So. Change the radical to exponential? Sure, I think that's a great start, Aisha. This would be x to the 1/2 times x squared plus x to the -1 like this, dx. I think that's a great start. Simon suggests distribute the rad x. This is the key idea. Great job, Simon. For sure, that's what we want to do. So when we distribute this rad x, remember, when you have two things to the same base and you multiply them together, then you add the exponents. So this is going to be 1/2 plus 2 is 5/2. So this will be the integral of x to the this will be the integral of x to the 5/2 plus 1/2 minus 1 is -1/2. So this guy looks like this. I think that's a great suggestion by Simon. Then what we need to do now is we need to find the antiderivative of each piece. So I'm going to add 1 to the exponent, which would be 7/2, and then divide by what I just wrote, divide by 7/2. For this guy, I'm going to add 1 to the exponent. That's going to be x to the 1/2, because -1/2 plus 1 is +1/2. And then I'm going to divide by what I just wrote, divide by the 1/2. Yeah, tack on a plus c there. Now, we had just discussed that dividing by a fraction is the same thing as multiplying by the reciprocal. So I have that happening twice here. So this guy is 2/7 x to the 7/2 plus 2 times x to the 1/2 plus c. And this would be our final answer.
Professor,
Yes.
from 5/2, how do you change into 7/2?
I added 1 to the exponent. So I'm using this, the integral of x to the n dx is x to the n plus 1 divided by n plus 1. So in my case, 5/2 plus 2/2 is equal to 7/2.
Thank you.
You're welcome. Is there any other questions about them so far? No.